Hey there, in this video I want to talk about the binary search method. This is sometimes called the bisect or bisection method. And previously we did the relaxation method, which required us to pick a guess near one of the solutions and hope that derivatives were just right, that we could just sort of iterate down to where we needed to be. And sometimes you can rewrite your equation in a way that'll work. Sometimes that doesn't really work out for you. But there's still a solution there, and there still needs to be some way to find it. Now go back to how you naively would solve a nonlinear equation. You would draw a graph of it, and you would look at where the lines cross. So why don't we just do a code version of that, basically just zooming in on our graph. As long as we have some idea of where the solution is, we could just zoom in closer and closer and closer until we see where the intersect is. And that's exactly what the binary search method does. So graphically, let's say we've got some kind of curve here, and that's our f of x. And just to be clear, we are writing our equation in the form f of x equals 0. And we're basically just looking at where it crosses 0. And in this particular case, hey, that would be right here. That's where my solution is. That's called the root. Now I want to figure out what value that is. So, and within some tolerance, what we can do is, as long as we can identify crudely where that is, we can say, well, I definitely know it's between two values, x1 and x2. And I want to put those as close to the root as I can. So this is kind of exaggerated. Normally you'd be able to put them a lot closer than what I just did. Now the one thing that is really important here is that the sign, SIGN sign of f of x1 is opposite the SIGN sign of f of x2. Because we need our program to be able to identify that the root is in between those 2 points. Yes, your eye can do it, but how does a program tell that the solution has to be? Well, if I have a number that's positive over here, and here's a number that's negative, then 0 has to be somewhere in between them, as long as my function is smooth. All right, so the way this works is we're going to take this interval and we're going to cut it up. This is the binary part. So we're going to cut it right in half, and let's say cutting it right in half would be, I'm just kind of eyeballing, let's say right there. And that's our new midpoint. Let's call that like xm for midpoint. And we would just literally find halfway between 1 and 2. Now looking at that, this is a place where the function is negative. So this would now become my new x2. And so now I will look between x1 and that new midpoint. So I'd cut that in half. And so now I've got a new midpoint. We'll put that like over here. And that's going to become my new x1. And we're going to just keep cutting this thing in half and in half and in half and in half and half until the x1 and x2 are so close together that we can say, yeah, good enough. We're within 1 part in a million or a billion or whatever your tolerance is. That's where the solution is. Now the beautiful thing about the binary search method is, since we're cutting our interval in half each time, even if your interval is huge, even if your interval is like 1,000 units from one side to the other, you can very quickly, in a not too many number of steps, get that really, really tiny because you're cutting it in half each time. So your only limit here is you have to be able to spot where your root is, and you have to have your function positive on one side, negative on the other. The one place where this can fail for you is if you have something called a double root, where your function just comes down and touches the x-axis. That can't be bracketed. And so binary search will not work with those kinds of roots. You'll need another technique for those. So let's try an example of the binary search. We're going to start with the function that we had before, x plus e to the negative 2x equals 1, and we're going to look for at least one of the solutions. First thing I need to do is write my function in the form f of x equals 0. So I have to type it a little bit differently than what I see printed above here in the markdown cell. Basically, I just want to move this 1 to the other side of the equation. So it's going to look like x plus exponential negative 2 times x minus 1. Okay, now we want to set up our binary search. So we need some starting values that bracket one of our solutions. And if we have our equation in the form f of x equals 0, we can call those solutions roots. So to bracket the roots, let's find the root that's about 0.797 that we know about from doing relaxation method in an earlier video. So, suppose I made a graph of this function. That'd usually be your starting point. I made a graph of the function. I can see there's a root there. So I'm going to start with x1 and x2 on either side of that. So clearly 0.5 would be on one side and 1 would be on the other. It's really important that when we evaluate our function f of x, that one of these be a positive number and the other one give us a negative number. That's what's going to happen here. Otherwise, we don't have the right bracketing to begin with and our method isn't going to converge. Next thing we're going to do here is run a for loop. So we'll do for I in range a lot. We're never going to get anywhere near 1,000 for these because we're cutting our interval in half each time. So really even 100 should be enough. Now each step here, what we're going to do is we're going to calculate a new midpoint. Let's call it xm for midpoint. And we do that by literally averaging x1 and x2. Now we're going to check to see, is the midpoint, does that become the new x1 or does the midpoint become the new x2? And we're going to do that by checking the sign of the function, SIGN sign of the function. So if the sign of evaluating the function at xm is the same as the sign of evaluating the function at x1, then that means that x midpoint becomes the new x1. So x1 will be set to xm. And if that didn't happen, then that means that x2 needs to be the new midpoint. Now we need to have some way to check if we've converged on our solution. What we're going to check here is if the space between x1 and x2 is very, very tiny. They're basically right next to each other. Guarantees the root is within that accuracy of that range. So we know that x2, we wrote this so that x2 is always the bigger value. So if x2 minus x1 is smaller than some tolerance, let's go 10 to the minus 8 for our tolerance. Then we can print our solution. Let's print the current midpoint, which is basically the same as x1 or x2 at that point, and then we're going to get out of here. And if we didn't get out of our for loop, then we'll print some kind of message to that effect. So we'll just print failed. Okay, and if we run this, here we go, converging to 0.797. I guess it'd be worth printing how many iterations. So let's make this a little bit fancier. So we'll do like x equals the current midpoint value after I, or really I guess I plus 1 iterations. So it took 26 iterations, cutting our interval in half each time until we could be accurate within 10 to the minus 8. So now if you're wondering, well, what's the built-in version of this? Yes, SciPy has one of these. It's not called binary though, it's called Bisect. So another name for the binary search algorithm is the Bisect algorithm. So it's optimize.bisect. And if we go check documentation, we want the function f and we want limits a and b. Tolerance here is set a bit stronger than what we set, but that's adjustable. Okay, so let's give it our function f. Let's give it the lower limit 0.5, and let's give it the upper limit 1 and see if it works. And we get 0.797, right? So it worked just like the code we wrote above. It's doing effectively the very same thing, perhaps a bit more efficiently. It's probably written in C or Fortran instead of raw Python, but it, same thing at the end of the day.